Chapter 6, Atmosphere and Ocean Interactions, Part 1. First, we'll start by looking at surface ocean currents, how they're driven by wind stress, something called Ekman transport. Then we'll look at subtropical and subpolar gyres. And finally, we'll look at boundary currents, what are called western and eastern boundary currents, and a thing called western intensification, which makes the western boundary currents move faster. As an introduction to this section, the general circulation of the atmosphere changes regularly with season. For example, we saw that the ITCZ has a seasonality to it. But the atmosphere changes irregularly over longer timescales as well. For example, there's floods some years and droughts other years. We have to look into the long-term patterns and their forcings to understand why this happens. 71% of the Earth's surface is water, and hence the temperature of this water tends to be the dominant force on the atmospheric circulation. So we've already showed how temperature gradients at the surface dictate pressure surfaces aloft and how that affects circulation. Since most of the planet is water, that water's temperature is very important. In other words, if you change the regional water temperatures around your location, you're going to change the regional circulation, and that's going to change the prevailing weather you'll see as long as that regional water temp anomaly persists. Surface currents. Winds push the surface waters into motion via what's called wind stress. Simply said, winds dig into the surface of the ocean and force them into movement. Wind drift currents are currents that are induced by this effect, usually limited to the first 300 meters in depth. Here's an animation looking at wind stresses over the course of a year. So we're looking at the northern hemisphere. Let's wait for it again. The northern hemisphere winter, we tend to have a very strong jet stream because of a strong temperature gradient across here, and therefore strong winds. So we're seeing a lot of wind stress in the oceans. Of course, this is going to drive big waves, but it also forces currents as well. And down in the southern hemisphere during their winter, same thing. Very, very, very strong winds down there forcing large waves, but also forcing a large current that actually loops around the planet, because this is the one part of the planet that doesn't have any land around a single latitude. Here's looking at the general surface currents around the Earth, and the first thing that should jump out to you is that there's these things called gyres, and they're found underneath all our semi-permanent high pressure anomalies. Again, relatively cold ocean waters force thermally high pressure. The high pressure forces winds to rotate anticyclonically, which means clockwise in the northern hemisphere and counterclockwise in the southern hemisphere, and that forces the currents underneath those winds to follow the same general pattern. So you have these large-scale gyres in all the major oceanic basins, what are called the subtropical gyres. Here's what's shown as the Ekman spiral. As wind blows across the surface of the water, by wind stress, it forces the first layer of water into motion. Coriolis will turn that water to the right in the northern hemisphere at about a 45-degree angle, but it varies a little bit. That surface of water will exert, by friction, the next layer of water into motion, which itself will now be under the influence of Coriolis effect, and it will turn it further to the right than the layer above it. That layer will then set the next layer into motion, which again gets turned further to the right, and so on and so forth, until about a depth of about 100 meters below the surface, the actual current's flowing exactly opposite as the original wind direction as a result of this effect. Now this is a really cool effect, but it's really hard to witness the whole Ekman spiral happening in the ocean. It's even hard to recreate it in a lab, but one thing is for sure is that the overall mass transport of the mixed layer, the layer that's affected by the surface winds in total, is directly to the right of the prevailing surface wind in the northern hemisphere. By that I mean if you integrate or add up all these directions and all the current movement within the Ekman spiral, the net direction is for the net transport of that mixed layer to be exactly to the right of the prevailing wind at the surface. This has major effects in places along the coast. California, for example, during their summer has northerly winds coming down from the north heading south. The Ekman transport of the mixed layer is therefore to the right of that wind offshore. To replace the water that's being lost offshore, it must come from the bottom, and to replace it in what's called upwelling. So that brings relatively cold, deep water to the surface to replace the surface water that was blown offshore. Alternatively, for a wind blowing south to north along a coastline to its east, the Ekman transport piles warm surface water along the coast. As a result, That water is forced downwards in what's called downwelling, and in this case you could expect warmer surface water to exist here because it's not being replaced by deeper oceanic waters. Now what happens underneath these semi-permanent high-pressure systems, which have anticyclonic turning, northern hemisphere examples shown here, the winds are spiraling around. Therefore, the net transport of the ocean water in the northern hemisphere is to converge it into the center of that subtropical gyre. That means you're piling up warm surface water in the middle of your gyre. The pressure in the ocean at any level is a function of how much water and air is above that point. So if water piles up at the surface in one location, in other words, a higher sea surface height, there will be more pressure in that water column in general. The pressure gradient force in the ocean, in the mixed layer specifically, is mostly a function of the sea surface heights as a result. One way to think of this, if the water column's higher some region and the water column's lower next to it, the water simply wants to flow downhill towards the lower water level. So in the center of the subtropical gyres, where Ekman transport has piled a bunch of warm surface water in the center, creating relatively high pressure in the ocean, the pile of water wants to flow downhill away from that high pressure anomaly. As it tries to do so, it gets turned to its right in the northern hemisphere due to Coriolis. The net result is you have a geostrophic flow, again, a balance between a pressure gradient force and a Coriolis force. This geostrophic flow goes around the pile in the same orientation as the surface currents were going in the first place. So the geostrophic flow around the pile reinforces the wind-driven circulation around these gyres. So therefore, that's why these gyres are so persistent and so strong. Here we're looking at the northern Pacific, and we have a subtropical gyre in the center of the ocean here, forced by, again, the prevailing wind circulating around it, but also by geostrophic flow. This tends to trap garbage that's floating at the surface within this gyre because, again, there's a net transport towards the center of the gyre, and it traps any garbage in there from getting out. So we have, in all the gyres, unfortunately, throughout the world, big piles of trash piled up within these gyres as a result of this converging surface water trapping it in there. So a question, if surface water, which is generally warm and less dense, converges into the center of the subtropical gyre and sinks very, very slowly, which it's forced to, the water just can't converge there for all time, it must be sinking slowly in what's called subduction, then why doesn't the trash that gets caught up in the gyres sink as well? Well, the simple answer is that trash has a lower density than the water, so it's positively buoyant. So it gets trapped there, gets forced by convergence into the center of the pile. Even though the water itself is slowly sinking through subduction, the trash is not sinking because it's positively buoyant. Now it turns out that the flow around these subtropical gyres is actually limited to around the mixed layer and doesn't affect the deep current very much. Let me try to give you an example here. At a level at the bottom of the mixed layer, no pressure gradient exists anymore, since in the center there's a lot of low density water, again warm surface water piled up, and at the edges there's a little bit of low density water and more high density water. The result is that there's equal weights at the bottom of the mixed layer. In other words, there's no more pressure gradient force underneath the mixed layer. So I'm trying to bring this out with a diagram here showing a big bulge of low density water in the center. So that pushes the hill up. Literally the sea surface heights are higher here, but also because low density warm water will actually push down on the higher density cold water underneath, you get a bulge underneath as well. In other words, it's stably stratified. It can't mix down very well, so it bulges downwards as well as upwards. At the edges of the gyre, you have a little bit of warm surface water, and right underneath, you have a higher density colder water. So as you go down to some level, say at this red line, even though you have more water above you, it's all low density water. And at this level, yes, you have less water in total, but you have some higher density water because it's colder combined with lower density water because it's warmer, and you end up getting no further pressure gradient at some level below the mixed layer. So therefore, you do not have any more pressure gradient force or geostrophic flow underneath the mixed layer. So a rather complicated way just to show you that this geostrophic flow around the gyres is limited to the mixed layer itself. Now, underneath semi-permanent low-pressure systems, such as the Icelandic and Aleutian lows, you know that the winds wrap cyclonically or counterclockwise in the northern hemisphere. The strongest subpolar lows exist where there is warm water, relatively warm, next to land surfaces in the northern hemisphere. So if you look at the winds spiraling around this, you'll find that the Ekman transport is actually going to be to the right of that wind motion or out of the subpolar gyres. So these subpolar gyres, based on the winds wrapping around them cyclonically, are forcing surface water out from that area. So a question, if most of the ocean's nutrients come from the deep ocean, which is true and that we'll look at in the carbon cycle specifically, then would you expect more nutrients in the center of the subpolar or in the center of the subtropical gyres? And the answer is the subpolar gyres, and that's because Ekman transports outside of the subpolar gyres. As a result, to replace the surface water diverging, water comes from the depths up to replace it in upwelling, and that brings with it nutrients and relatively cold water. Next, we'll look at what are called boundary currents. You can have two types. You can have a western and an eastern boundary current, and they can be cold or warm. Here's shown as a boundary current, an eastern boundary current, because it's along the eastern boundary of the Pacific Ocean as it hits the west coast. If it's moving equatorward, as this one is doing, it's a cold current because it's taking Arctic waters and moving it towards the south. Here we're showing with a red arrow a warm boundary current, and it's a western boundary current because it's on the west side of the ocean. Again, it's a warm current because it's taking equatorial water and moving it poleward. All subtropical eastern boundary currents are cold, as shown here. Winds again are forcing the current into motion anticyclonically clockwise in the northern hemisphere, giving you a cold current called a canary along the coast of Africa. It also is giving you a cold current called the California current along California and Baja. In the southern hemisphere, same thing, but the subtropical gyres rotate the opposite direction because so do the high pressure systems that form them. So again, you end up with eastern boundary currents that are relatively cold, taking polar water, mixing it towards the equator in all these oceanic basins. At the same time, if you go to the western boundary currents in the subtropical gyres, they're going to be moving warm water poleward. The Gulf Stream's an example, the Kuroshio's an example, and all these currents down here in the southern hemisphere as well. Now, since the subpolar currents rotate the opposite direction, all subpolar eastern boundary currents are warm. In this case, the Alaskan current is part of the Aleutian formation, and the Norwegian current is part of the Icelandic low, and that's moving warm water poleward again. All subpolar western boundary currents are cold. In this case, the East Greenland current, moving Arctic waters towards the equator. Now, it turns out that the western boundary currents of the subtropical gyres are not only warm, they're also thin, deep, and fast currents. While the eastern boundary currents of the subtropical gyres are cold, but also wide, shallow, and slow currents. These differences are ultimately caused by the rotation of the Earth. And here's just looking at how they look. Here's the Gulf Stream, a very fast, thin current, but also very deep, and it's also warm because it's from equator to pole. And here's the Canary Current down the west coast of Africa. It's cold because it's going from pole to equator, but it's also wide and slow. If you're interested in the dynamics that cause these differences in speeds and depths, I'm going to leave it to you as an optional exercise in your online program. Here's the Gulf Stream just showing sea surface temperatures from the Gulf Stream as it goes along the coast of Florida, gets banked off over Cape Hatteras, and wiggles its way out towards the mid-Atlantic. The Gulf Stream is a very, very fast-moving narrow current that transports a whole lot of water poleward, specifically warm water. Here's an example of how anomalous that warm water is offshore. So even in relatively cold climates, in this case Martha's Vineyard, Massachusetts, you never quite know what might come up swimming up that warm Gulf Stream. Here's a 1,200-pound tiger shark that was caught well offshore in a shark fishing contest, where I want to make the point that this species prefers warm water. You almost never find it in cold water. As a result, the only reason it was there is because the Gulf Stream waters are so warm. The sad thing about this, besides the fact that it's a shark trophy contest, is that they went out so far to get this shark into the Gulf Stream that by the time they got back, the contest had ended 5 minutes earlier, so it didn't even count towards their prize. You can see here in this map that as the Gulf Stream banks off the US, it heads off towards Europe. in what is called the North Atlantic Drift. Because this water is so warm and the prevailing winds are from the west to east, it causes regions of coastal Europe to be up to 20 degrees Fahrenheit warmer on average than other Canadian regions at the same latitudes. Key points from this section: the world's surface currents are primarily driven by wind stress. The Ekman transport of the mixed layer, down to about 100 meters depth, is to the right of the primary wind in the northern hemisphere and left in the southern hemisphere. The subtropical gyres are underneath semi-permanent high-pressure zones and thus rotate anticyclonically, which means clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. Ekman transport forces the convergence of nutrient-deficient surface water into the center of these gyres, regardless of the hemisphere. On the other hand, the subpolar gyres are underneath semi-permanent low-pressure zones and rotate cyclonically, counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. The big subpolar gyres are in the northern hemisphere, where there exists the land-sea contrast needed to form them. Divergence of the surface water in subpolar gyres by Ekman transport leads to the upwelling of nutrient-rich deep water that's also cold. In the subtropics, western boundary currents are warm, thin, deep, and fast currents, and eastern boundary currents are shallow, cold, wide, and slow currents, and both influence regional climates downwind of them.